Hello everyone, it's June 15th. Alright, it's actually very late right now. 9:57. Well, I had meetings in the morning, so I couldn't do it as a morning session, so I have to settle for the evening ones. Mainly today I was doing a homework today. It's whenever the homework is to write a report, it's always going to be awful. And for this class, I have to write 3 reports. And the first one, I just didn't really pay much attention to it. I just did it the way I thought the report should be written. And then I was instructed that that's not how it's supposed to be written. You have to write it in a very official way, with introduction, methods, results, discussion, all that. Like, oh my God, not again. I remember I had to do the same thing last semester with reinforcement learning, and this time with computer performance modeling, it's the same thing. So yeah, I complain every single time about this, but in fact, in retrospect, it's not too bad a thing. I think it's not too bad because you explore for a project. You explore in the project. You try to understand what the project is about. Do data analysis or whatnot. And at the end, it's actually a good thing that you have to write it up, in a very formal way. But it takes time and it takes efforts, and I definitely do not like writing this type of things, right? But I changed my mindset, right? I was very reluctant to start writing, but then I changed my mindset. I was like, I like writing blogs, right? Writing like tutorials, all that type of stuff. I find fun in it. Why don't I just write it like that? Right? You don't think of this as like a report on a project. You have to be like very formal all the language. No, just think about this as a tutorial. A tutorial that you did something you want to share with other people, and just to write a tutorial in a framework with introduction, methods, result, discussion like that. Once I have that mindset, things become much easier. Like the language I use is much smoother. It's just like how I would use when I write a blog on Medium. So everything becomes more palatable. So I just finished about I said like maybe 10 minutes ago. I just finished, submitted the homework. Man, this semester is a lot of work. Anyway, that's enough of me complaining. Let's take a look at what we have today. Matchsticks to square. Feels like a, how should I put it, an IQ test. Oh wow, I have 5 hints. Okay, you're given an integer array, matchsticks. Oh, by the way, yesterday the problem I said I'm going to look into the knapsack. So I did look into the knapsack. So there are many types of knapsack, and there's one with a limited number of bags you can choose, and this one is actually the easiest to solve because you only have to you pick any all of them are dynamic programming, right? You pick any bag, and then you can compute the maximum that you can get with all the remaining bags, right? It's actually fairly simple. So that's one type. And the other type is called 0-1 knapsack. That's like you only have one bag for each type. So once you pick that bag, then you cannot pick again. So that one can be done in a 2D array, which means you have to consider 2 things. First is the weight. You have to consider the weight, and also you have to consider the index of the bag that's currently being considered. So like 2D array, but it can be optimized into a 1D array DP. So that's the second. And a more difficult one is called it's also 0-1 knapsack, but we have we have restrictions on, wait, what do we have a restriction on? We have the restriction on the total number of bags allowed. So we not only have the restriction on weight, but also the total number of bags allowed. So this just means we have to add one more layer to the DP, so it can be solved with a 3D DP table, but the basic concept is the same as the no restriction on the number of bags. And finally, there is one knapsack problem called fractional knapsack, which means you can take fractions of each bag. So it doesn't matter. So you don't have to take the bag as a whole. You can take a fraction, like a third, a fourth, doesn't matter. And that one is actually the easiest because you can solve it with greedy, right? You solve it greedy. You basically take the bags with the highest value first to fit as much as you can, and after you finish that, you take the second highest value to fit as much as you can, because you can do fractions, so it doesn't really matter, right? So now, after listening to this and thinking back on the problem yesterday, we use greedy, and then we take as much as we can on the highest value. Well, I should backtrack. It's not highest value; it's the highest value density. So it's the value divided by the weight. So the value density, the highest value density. That's the one we should take. So like after hearing about this, it's kind of, yeah, I think yesterday's problem is actually a what should I put it? Actually a different version of the fraction knapsack, right? So the difference is in the question, what we have is each box have certain number of units, right? And each unit has a value, right? So we can think of the number of units as the weight, right? And it's a fraction. You can take yeah, I think wait, you can take, yeah, you can take fraction. You can take however many boxes you can take, right? It doesn't matter. A unit, a box has. Wait, I forgot. I was able to figure out yesterday. Hold on. I mean, maximum units, right? You can take 2 boxes of the second and a 3 box. All right. So we say we're going to take 5 boxes and 2 box. The next one is number of units per box. Yeah, so we consider this whole thing, right? This whole thing as a bag, right? This whole thing as a bag. And the number of boxes is the weight. And the number of units per box is the value density, right? So this becomes the fraction knapsack. So we can take a fraction. It's just the fraction. You just can take like a 1 box, 2 box, 3 box, 4 box, 5 box. So these are just the fraction. So we need to take the fraction in order to fit the total truck size. So this is a disguised fraction knapsack problem. That's why we can solve it using greedy. So yes, this is right. Kind of get my mindset back. So yeah, that's what I want to say about this problem. All right, let's go back to today's question. All right, we have the matchsticks, and each one is the length. You want to use all the matchsticks, so it's all of them, to make one square. You should not break any stick, but you can line them up, and each match must be used exactly once. Return true if you can make this square, and false otherwise. Basically, what it's trying to say, is it possible to have combinations of the matchsticks such that we can arrive at four values that are the same, right? And this is false. You cannot form a square, okay? So the matchstick length is 15. Ooh, 15. Interesting. So 15, we can explore a lot more options in the algorithm because it's a very low value. So what we want is 4, right? So we can add them together, divided by 4, so we know the length of each. That's 12, that's 16, so we need 4 each, but there's no way we can get 4 out of these. Yeah, a 3, 4 out of 4 3s is not possible. Okay, so we know the length of each. Then what? Well, then if we have any value that's larger than the length, then it's immediate false, right? Because we cannot break it. If we have the same value, that's good. We save it. We record how many. We record how many we have. And if we have lower, then we need to accumulate them, right? We need to accumulate them. So the basic question is, how do we accumulate? We can sort. I only have 15, so we can sort it, right? We can sort it, and then we go from the higher to lower because it's easy for us to reject if something's wrong. So we go higher to lower. If there's something larger, then we reject. If there's something the same, we count how many we have done. So we count 1, 2, 3, whatever. And then when we have something that's not fitting, then we can go, it must be from the end to the other end, right? Yeah, actually it's more complicated than that. It's more complicated than that. Isn't that like I won't say a 3 sums, right? It's just a multi-sum, right? Multi-sum, which is possible. Like if we encounter a value, right, and its value is smaller than the length, so we know how much smaller it is. Well, every one has to be used. That means we must find something, right? We must find something that fit into. Is it possible, like there are like multiple ways for it to work? Let me think. We're talking about like multiple ways for it to work. Like if a value can be fit with another value. No, there shouldn't be. There might be multiple ways, but if you can find a way, then it shall be good. If it can fit, then it shall be good. Yeah. So any way that you can fit shall be good, right? Any way you can fit shall. Yeah, because every single match has to be used once, and if there's any way that we cannot fit, then it's definitely not good. All right, so we hit a value and we say the length is 2, so we say if there's another 1, and boom, we have. So that's good. Then we're done. And here length is 4, and 3 needs a 1, and a 1 does not exist in it. Then we say it's bad, right? But we will have a situation where, say, we have to have 3 line up, right? So we say, like, if we have the 1, 1, 1, 1, 1, 3, 3, 3, right? 1, 1, 3, 2, 3, and then we say 1, we need a 2, but we don't have a 2. If we don't have a 2, if we don't have a value in it, then what? Then we keep searching. We say, okay, we don't have. So that means we need to get to a 2, right? A lower value. So we keep searching, right? We keep searching for the remaining, and until we find someone that's smaller, then we say, is that possible? Hold on, that seems to be very convoluted. I have the largest value, right? And then we need to find how many. What would be a good way to solve this? We know the sum, right? We know the sum, and I think we just do, we know the sum, and we try to look into each value, right? We try to look into each value, and we try to look into each value, and we try to say that if this value is smaller than the length, and then we do the value minus that, so that's the remaining value we need to find. So we run through the same thing. Yes, we run through the same thing, and just try to see if we can find anyone to fit. And the first one we can find that will fit will work, right? It will work. Once it's done, we do it a second time and do that might work. Like, we can rely on the first fit, right? We can, because the requirement is everyone has to be used exactly once, right? So if a match can be used in one way, right, then if it fails, then it's a fail. Like, if we want to rearrange it, it's not gonna work. Is that true? Like, if it fits one way, and then what I'm saying is it possible that if a match that fits one way, so like if on one side we use some type of arrangement, but then because we used some match and then the rest doesn't work, is it possible that if we rearrange them, then it will be? No, I don't think it's possible. If the rest doesn't work, that means something just is missing, right? Something is missing. Something is missing. Well, something missing, it won't be too short. It's going to be like this, right? It's going to be like this. It's just doesn't fit, right? If it doesn't fit, then I change. It won't change the fact that it doesn't fit, right? If I have one line that fits and another line that does not fit, then if I do any type of swap, that doesn't mean that it will become fit. So yes, I think this is correct. I think this is correct. But let's take a look. Okay, here we go. So let me say make square, right? So what we're looking at is want to first make a sum. So this is going to be total length, right? Total equals sum matchsticks. if total 4 cannot be divided by 4, return false. Right? So now total can divide by 4, so we say side equals total divided by 4. Right? Then what we say is if max matchsticks is larger than side, return false. So these are just simple cases that we check. And then we need to turn that into from collections import counter, and turn that into a counter, right? So, oops, yeah, mess around with the indent. So when I say counter equals counter matchsticks, right? And then we're gonna go just round by round. We have 4 rounds, right? You can say for this in range 4 rounds. Each round we're gonna have current side equals side, right? To start. Then we're just gonna loop through how do I do this? We're gonna say for current, or just pick any value inside counter, right? We pick any value inside a counter, and then it must be smaller or equal to. So we say the remaining, and then the remaining will go back. And we say we're going to pick any one in the counter, so we just do a range in the counter, right? So we do a range in the counter, and do 1, and if it's larger, then we moving on until we find one that we can do, and find one until it becomes 0, right? Until it becomes 0. For each one, we'll go through it again. It becomes 0. And once it's done, oh, we need to copy the counter every single time, right? Because if it fails, well, if I fail, yeah, we have to backtrack, right? Yeah, it seems like we have to backtrack. It is possible that we will fail, and we're going to iterate through every single one of them. So I think we will have to backtrack. So we have to define a backtrack. Def backtrack. Right, so backtrack is going to be, actually we're gonna do it after the counter, so we don't have to worry about passing the counter. So just as the current side, right, the current side, and we say if current side equals 0, then return true, right? Positive link, return true. Otherwise, we say if current side is smaller than 0, hold on. Now we're just going to have to loop through every single one, right? So we'll just say on the current side for key value in matchsticks.items, right? Not matchsticks.item, counter.items. If v is larger than 0, which is the count, if v is larger than 0 and k is smaller or equal to current side, right, then we do backtrack current side minus k, right? And then we're also going to do counter k minus equal to 1. Maybe I cannot get v out as well. Yeah, I think it's fine. So counter minus equal to 1, and then we say if backtrack is successful, right? If backtrack is successful, then we're going to return true, right? If it's not successful, then we're going to say counter k backtrack, put 1 back, and then we go try the next one. And once everything has been tried and we do not return true and return false, and we cannot do, right? So that's the backtrack. So here for this in range 4, I think what we need to do is just going to be, we can return all, right? All has to be true, or what? For this in range 4, we'll do it 4 times, and we're going to backtrack side. Right, I'm going to backtrack side for 4 times. And each time we're going to update this. Alright, let's take a look, see if this solution works. So first test case is 1, 1, 2, 2, 2. This one will return true. Second one is 3, 3, 3, 3, 4. This one will return false. Okay, so this is going to be matchsticks, and this is going to be make square matchsticks. Try it. Both pass. Alright, let's take a look here. I'm not worried about this shouldn't be any timeout concern. Only concern is the accuracy of this. So let's do, say, just 1. That should be a false. Because, oh yeah, that should be another thing. At least you need 4. So if total is this is false. If max is larger than this is false. Alright, and then if len, if len matchsticks, right, matchsticks is smaller than 4, that's going to return false. So we have to at least have this, right, and this can be false because 10 is not divided by 4. So this can be handled by all these cases. And actually I want to be clear. So these are the trivial cases, and real case, non-trivial case, trivial. All right, so let's see. Can we get to, I don't know, 4? 5, 5. 5, we need 5, right? 5, 2, 3 again, and 5. This should be this should be true. Oh, oops. Oopsie doopsie. We have a problem. Houston, we have a problem. Doesn't matter. We're here to solve problems. Let's see what goes wrong. Yeah, this one shall be true, but we're returning false. Okay, why is that? Where is the false? Shouldn't be any of these. These are fine. So I think I can. So what we are going to do is I'm going to print temp true, true, false, false. Alright, I'm not going to do it this way. This is not going to help. So when you say for this, range 4, now then return in range 4 and say backtrack side. Alright, and I'm going to print counter. And print backtrack this, print counter. Alright, let's take a look. First is true. We take away 2 and 1. Hold up. We take away 2, 1, and 2. We take away 2, 1, 2. Oh, it does. It does affect. But take away 2, 1, 2, that's 5. But the remaining cannot make 5. Oops. So it's not correct. Okay. Okie. So that's not right. And how are we going to do this? There are a lot of possibilities, right? Like, can we say if one round is bad, can we like do it again? What do you mean, like do it again using a different order? I don't know. I mean, say it comes in, so I got 2, right? And then 2 is and then false. And then this is a false, right? So if it's a false, can we backtrack again? That just means one of the things that done before is wrong. Oh. Let me think again. So we're given a list of only 15. Come on, think about it. We're given 15 numbers at most, 15 numbers. And we want to know if it is possible to combine in any way we want to combine this in order to create, right? In order to create 4 values of the same size. 4 values, right? I kind of want to lean back into the sorting. Okay, we sort, and after we sort, we go with the largest first, right? And then we say the largest. We already checked the triple case, so the largest will be smaller or equal. So if the largest is equal to, then we just pop it, right? We just pop it. I don't care about it anymore. And if it's smaller, then because it's currently the largest, right? If it's large, then we should always try to match that with a small one. Oh, why? There's no reason. There's no reason. And this is a typical example, right? So And of course, if we go to large and small, it's going to work. But why? After we sort, why can't we do large by itself? Well, if we do not do large and small, okay, that means, let's say the large is not matched with the max is not matched with the smallest, right? This is the premise, right? Current premise. If the largest is not matched with the smallest, that means large must match with something else, right? And if large match with something else, which is larger than the smallest, and it is still, say, within the limit, that means the small one will never have a chance to reach the limit. Is that right? Yeah, if you think about it, I have the max, I have the mean. If I do not pair the max with the mean, and then we pair max with somebody else, and if that can be paired, right? If that can be paired, that means we have a value where the max with not the mean is smaller than the current side, right? Which means the mean value will have nobody to pair with, even to reach the current side. Therefore, the optimal solution is always have the max to pair with the mean, right? And we can actually do it. The max pair with the mean, we can create a new value. And then we look at this new value. If this new value is smaller than the side, then we're going to pair that with the mean again until we can find, until either we break or we reach, right? So we always try, so we create, so yeah, the largest has to be paired with the smallest. If it does not, then it's guaranteed that we will not be able to use every single match. So when the largest is paired with the smallest, we can create a new value, a new largest value. And then again, the new largest value has to be paired with the smallest. Okay, let's try that method. And that method will definitely work for this one. No question about it. But that just means we don't have to do the counter. So there'll be no counter, right? Yeah, I feel like the counter is not going to work. All right, so we're going to sort. All right, matchsticks.sort. All right, I'm going to sort it. Then we already eliminated all the possibilities. So we're going to say from back, we're going to pop all the largest values, right? So we're going to say while matchsticks, right? It's actually a stack. While matchsticks, if matchsticks minus 1, right? The back is equal to side. Actually, these two sum. I think this one we can do it here if it's larger than side. If it's larger than side, then it turns false. If this is equal to side, then we say matchsticks.pop. If matchsticks minus 1 is elif is smaller than side, right? You can actually do elif on each one of them just to make it elif, and then this one can be else, right? That would be easier. So else it's smaller than side. If it's smaller than side, then we say matchsticks.append oh, we have the pop left as well. So we need a deck. We need a deck. So I'm going to say a DQ, not deck, equals deck. Right, so sort it. So we say while DQ, if DQ, yep, dot pop. And then we're going to append DQ dot pop left plus DQ dot pop. So the largest and the smallest, and then we append to the end. Alright? And then we go back, we check. If it's not, and then every time. Okay, so everything's good, then we're going to return true. And this one, none type is not iterable. Which one? Oh, it has to be sorted. I have a DP, there's no DP, only DQ. Yep, it's on pass. Pretty sure these two are pass as well. Okay, so there's a new solution. It's completely different. Yeah, we're using deck. That's actually we have to include deck. I don't know. You wanna try? Let's try. Pending, judging. Hey, we got a wrong answer. So deck doesn't work. Alright, I already see a wrong answer, so let's take a look. It's not as easy as I thought. Okay, what is this one? Expected is true, but I return false. Okay, it's fine. Let's take a look. Alright, so at 12, I'll actually just print. Let's take a look. So on the print side, so side has to be 12, right? And we say we do 5 plus 3, 8, 8 into plus 4. And the largest has to add to the smallest, right? But after I added the next round, there's no requirement. Okay. Hold a second, let me think. So we have the original, right? This is the original. And we have the largest and the smallest. So largest has to pair with smallest, so we get a new value, but we don't put it back. No, we don't put it back. Let's say we put it in a new place. Right, we'll put it in a new place. And then the second round, we have still the original largest and the smallest, right? And we say the original largest and smallest, we still gonna do 5 plus 3, 5 plus 3, 5 plus 3, right? And then we have the 4s. Oh my god, how do we handle this? Alright, let's say we have 4 sides, right? And for the 4 sides, for each side, I say I'm going to do the max plus the min, right? The max plus the min. And after I do that, I say, okay, that's that. And for the remaining, right, it's the same, max plus min, max plus min. So after we've done all these, then we pull the values together. So we're doing 4 rounds, so we make sure that each round has the original matchstick tried, because for the original matchstick, we have to make sure that the current largest must match with the smallest, right? Otherwise it's not going to work. Someone is not going to work. That may I don't know. This is my idea, right? The largest has to match with the smallest. If not, then the smallest, the largest is already gone, and the smallest. Yeah, if we're a 2 system, that's true. But what if we have more? The large plus the small. The large plus the small. It feels like we're gonna have to do a lot of trial and error. Largest. And the thing is, there's so many different combinations. Even 15, we have a lot of combinations. I know what you're thinking, but that's just crazy, right? That's just crazy. I don't think that's going to work. We have to analyze it. Okay, scratch that. Let's just do, let's say, we'll pick 5, right? And then we can pick another 5, and then good, and then we'll try to pick again. And we should pick 5, doesn't work. 5 doesn't work. 4 doesn't work. 4, 4, 4, 3, 3, 3, 4. So we tried to, that doesn't work. So 5 cannot pick 5. So 5, we pick 5 is not going to work. And pick 5 is not going to work. We're going to pick 4, right? And then we can pick another 4. That is going to explode. So we cannot pick 4. So we're going to pick 3. That works. So we save that. And then next round, it also work. We'll save, all good. But what if in a round, and we keep going, and it failed, right? And we have a failure. Like a depth first search, right? We hit a failure. If we hit a failure, then say we're going to backtrack. How do we backtrack? So we backtrack to the start of this. But we backtrack, try all the other possibilities, and then they all fail, right? And they all fail, and that means we have to backtrack into the previous. We have to keep the stack for all of them, like even if it succeeds, then we have to keep going. Hold on, even if it succeeds, right? It succeeds. So what we're going to do if it succeeds? Like we don't, well, it does not succeed. It only succeeds when all of them are found, right? So if we do backtracking, we start from 1, right, and then we try to go to the next one, every single one, and then eventually we'll hit a point where this thing becomes 0. If it becomes 0, the side is 0, then we add the weight, the number of sides that currently being considered. And then what? What do we return? Shouldn't we like reset? Or we call it again? Two levels of backtracking. On the top level is to find a successful match to the side. And so once we find that, we go to the next level of backtracking, which is we're going to call, so what the function will look like. So the inner backtracking is just to find the one that works, right? As it works, then that's good. We stop right there. And then from that point, we're going to call again. Call with it's still backtrack, right? Call it with a backtrack. But just with a smaller hold up. Backtracking. And once we're done, right? Once we call this function, right? We call backtracking, and once the backtracking with that, and then as this, and we do this, and then what? -1. Then we keep going. How do we keep going? Like we start from the front again? We do the backtracking again? Well, I think it's going to be backtrack. So I'm going to pull up the backtrack. I think no, that's the last submitted. I didn't save the previous one. Probably I can do Control Z. There we go. Let's try this one more time. Apparently this one's not working, so I'll try it again. Okay, so the backtrack, we need the side length, right? We also need so we have current side length, and we also want to have backtracking is current side length and side completed, right? We say if current side is this, then side completed plus equal to 1. If side completed equals to 4, right? If side completed equal to 4, now we return true. This is the one we return true. Otherwise, we're just going to be backtracking again. So we're going to backtrack. Current side will be equal to side, which we can pull it in, and then side completed. We're going to backtrack again. So basically say if a equals to 4, then we go true. If not, then we're going to do this. Say if backtrack, this is good, then we return true. right? Otherwise, if the backtrack failed, right? If the backtrack failed, what do we do? If the backtrack failed, that means um, that means site completed we don't have to change because I didn't really site complete x plus 1 and then site completed here. Site completed is fine. Then we just return false, right? So in here, there's nothing we can do. It's just telling us that the current site equals 0 will still give us false. And then we do this, if v is this and the k is this, counter -1. And if backtrack this with site completed, number of site completed, that is true, which will only happen if this happens. And then I return true. Otherwise, it's false. So I added this, try it again. Try it again. And then this one we can just return backtrack side, right? And then the 0, and 0 completed. And we start current side. I'm not sure. Try it. Oh, this one passed. Oh, they all pass. Maybe that is the trick. It's just a complicated backtracking. Huh. Alright, let's try this one then. Well, at least they passed the 2 test cases. Let's test both complicated test cases. Alright, let's try this one. Pending. Judging. Oh Lord. It passed, but dear me, it's very slow. I mean, yay, we got it, but it's very slow. I don't want to look at it. Ay, ay, ay. Alright, so this one passed, but it has very terrible runtime. Alright, so yeah, the problem is harder than I had expected. It is easy to see, easy to filter out all the trivial cases, right? And obtain the side of the final square. Then the problem becomes to judge whether some combination of the values in matchsticks can form sums, can form 4 sums that equal to side. The current solution is backtracking, right? Is backtracking. Basically, we start from any value in matchstick, right? In matchsticks, and see if we can successfully construct the square. If not, we backtrack on all of our previous decisions and try a new route. I do not know the time complexity for this. This could be very hairy on time complexity. Right? Yeah, when it fails, when one round fails, and it's ON, right? ON. But if one round fails, we have to backtrack. Right? It's false. And then false, we'll backtrack to the start and have to do it again. It depends on how many times we have to do the backtrack. Actually, I don't know. I don't know the time complexity for this. But we have runtime very slow. 3,544. That's our runtime. Milliseconds, or 6% ranking. Well, what do you think? Is that the backtracking side that has the problem? But these are fast. Yeah, it's definitely the backtracking side. Maybe look at cache. We feel like we are solving problems that has repeated. How do we cache this? Well, think about it. You can cache it as the current side, right? The current side, the current I'm visiting, and a number of sides that's been finished. Next time I visit, that will be slightly different. 15. 15. 15. That tells me, that gives me a hint of a bitmap. 15 is a bitmap. So it is possible to represent the states of which one gets chosen, right? So we can use a bitmap. Initially, everyone is 1. Everybody is 1. And then when we choose 1, we set it to 0, right? And then that's the state. So we have the state. Right? That means we have the state and we have the current side. So if I have a state with the same current side and with the same side complete, I wanna see if it is real. Like, try this one. How do we see that? How do we see that we have repeated? I don't know. Let's print current side completed on the counter. Right, current side completed. We do have 0, 0. Have 0, 0 again. 5, 1. 5, 5, 1. 5, 1 again. But does the counter has the same state? 0, 0. 3, 2, 4, 1, 5, 1. 3, 2. 3, 2, 4, 1, 5, 1. No, it's not the same. How about 1 1? 3 2 5 1. 3 2 5 1. 3 2 5 1. Oh yeah, look at this. 1 1 3 2 5 1. 1 1 3 2 5 1. So we are repeating. Oh, okay. Good math. Good math. And definitely. So memorization in backtracking. Yes, that is going to save time. So we can do almost exactly the same here, but we actually don't need, right? We don't need, so we do this, 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 this. Nope, we don't need this. So we basically just say, all right, we're gonna do LRU cache. From functools import LRU cache. Right? So we're gonna say here at LRU cache max size is none. Right? So we're gonna backtrack current side completed, and the state. Right? The state. So here's what we're gonna do. Current side is 0. Side completed plus equal 1. Yeah, we can also pass in the original side. That's fine because it's going to be cached anyway. Side completed plus 1. Second is we're going to do true. That's good. Otherwise, we're going to do if it's not 4, then we're going to do side and state. And we don't change the state. Same state, but we're going to pass a new side in. Otherwise, return true, right? Or return false. Now, here is the meat part. Current side is not, right? So we have the state. So we're just going to say, I'm going to pick any one. So we're going to just go through every single one. So for I, right, we're going to say for I in range 16, right, in range 16. So 0 to 15. 0 to 15. Move 0 times. Move 1 time, or move 15 times. So when I say if it is 1, right? When I say if I 1, move I times state and this is not equal to 0, right? If it's not equal to 0, then we can use that value. So we say and the k is going to be smaller if this and matchsticks I hold up. So matchsticks I only have 15. The length is 15, so the I is actually has to be 15. Matchsticks I is smaller or equal to current side, right? That's when we can say, remove it, state, Now I'm going to say backtrack current side minus matchsticks I. Right, and actually do this. And then side completed, we don't change. And then the state. The state. Exclusive OR 1 to I. Right? But then we don't change the state. So let's say if shoot. Let's put it back up. Right, we'll say if this, then return true. If not, we don't have to backtrack because we didn't change the state. We calculate the state. We don't change the state. So we don't have to change anything. That means just we have to keep going to the next possible for the current state. And then when all fail, return false. Right, so now in a backtrack, 0 and 1, 16 times minus 1. That's going to be 15 ones. I'm pretty sure we have to do this just in case. Okay. No name means solution. I think it's solution 2, right? Yeah. Name it solution 2. Trouble. List out of range. Huh. How is list out of range? I is 0 to 14. Oh, shoot. No. Alright, we have a length. It depends on, yeah, my bad. My bad. It's completely my bad. N. Alright, so this is n plus 1 minus 1. And then in here, that should be in the range n. Pass. Okay. Everybody pass. Alright, let's see. I have high hopes. I think this one's gonna be really good. Hey, okay, I think this one will pass, and I'll be very proud of myself because finally, after so many fails and practices, I was able to. Actually, I think this one can be OR, right? Or backtrack this, then return true. Yeah, because it's short circuit. If it is true, then either control it. Yeah. Let's go. Accept it much faster. Ooh-wee! We're talking about 132 milliseconds. Yes, this is the solution for this. So we can save two lines. Yep. So memorization. I'm very proud of myself to have noticed that we can use bitmap to represent the state of which matchstick has been used. This way, we can easily use RU cache to memorize the scenarios that have been encountered before. The giveaway is the length of the matchsticks array being 15. The max being 15. So with this, and we can say the runtime is going to be, it's actually 01, because the worst case scenario is each state is visited once. So runtime is 2 to the n. Wait, is that 2 to the n? Yeah, it's 2 to the n, where n is the size of the length of matchsticks. But since n is smaller or equal to 15, the runtime is very fast. We had 132 milliseconds, or 73. Yeah, we'll go from 3,000, right? More than 3,000, 3,500 to 132. Yeah, that is the solution. Okay. Now it's time to check. Medium, definitely medium question. No doubt. Yeah, it's no doubt it's a medium question. Because the only trick is, like, if you can figure out the backtracking, they allow you to solve it. I mean, if they have a cutoff on a time, say like 200-300 milliseconds, which means you cannot use the naive backtracking, then that might be a difficult one. But this one is fine. What subset of the TI belongs to? We tried all the options. DFS, yes. Oh, it's a long DFS. 4 to the n. Dynamic programming. To the 15. Oh, we can go even faster. People saying this has to be hard. I would be more than happy for this one to be labeled as hard, which give me more boosts and confidence. Yeah, I think the idea is the same. DFS index, they use index. Index equals to L. They don't have to sort. Sums 0, 1, 2, they're all equal to possible side. For I in range 4 times. If this plus nums index smaller than possible side, recurse sum, and then the next, and the reverse. Yeah, this part is, this is just the typical. Yeah, I made it more complicated right here. I made it more complicated using the counter, but it's the same. It's the same. You just need to have 4 times. Yeah, we just need to have 4 times, and if and it succeeds when all 4 succeeds, right? Otherwise, you return this. Yes. Total of n sticks for each one of these match sticks. Because we have a total of n sticks, and for each one of those match sticks, we have 4 different possibilities for the subsets. That is correct. Dynamic programming. This considers dynamic programming because I memorized. How the site can be constructed. There are multiple ways to use the same set of match sticks to land at different recursion states. What all match have been used and which are remaining? That's multiple different. So we have to use another one, right? Number of sides have been completed, yeah. I will always consider that arrangement forms and then second has been used before. Are you saying we don't need the current side? They don't use the current side here either. But this is the current side. Sums I is the current side. Don't know, is it 4 equal halves? Completed 4 on any point in time. LeetCode. If side equals 4, then it's going to match available. Add match to match sticks used. The result equals remove match from match stick used. Add match to match sticks used. Yeah, bin mask. Okay, they use bin mask as well. That's because total is 0. True if not, environment. Return this answer suffice. I think this is polluting my mind. What the heck is this? What? What the actual heck? Oh, hold on. Why did it do -1? It was 3. Oh, yeah. I don't have to go to this. This is just, that was wrong. Just n. Well, n times 1, 2, 3, 4 n is already, yeah, so for n times, that's good enough. And we can do equal to 3. Yeah, we're going to equal to 3. I like mine. And we iterate our original match sticker to sum up the values. Did you do that? Oh, shoot. I did. This is ON. No, I don't think so. No, I think it's just 2 to the n. Because I only... Because each one, I create a new state, right? And then we visit that state. And then if that state has visited before, then we just go back. So basically, yeah, I think each state is visited. I stick with 2 to the n because I think each state is visited once. But this is the trick. Yeah, we have a trick. I don't like this. I don't want to understand it. It's polluting my mind. Yeah. Oh, let's see. 6 millisecond BFS. Subsets. Oh, they only do a mask. Yeah, that's what I think. 2 to the n, right? Oh, with ON transactions for each one. Ah, okay. Now this makes more sense because if you think about it, we have a mask, right? We have the state. We have the state. So we say each state is visited once, but in each state we go through n times. That's true. That is true. Okay, so it's the same if this is this, right? Now equal to 0. Oh, I can just say, yeah, I can do this. I don't have to even do this. I can do this. Next, B plus DFS. Alright, and if this is larger than 0 and this smaller than the basket, do I have 4? Oh, that's the side. What do we return? DFS equals 0. Return nab plus nums j mod basket mod length. If it's possible, t is a remainder when we divide sum or use the numbers so far by basket. How many we need to put in each group? Ah, I think I know what it's trying to do. mod basket. So that's the sum of everything. You sum of everything and then you mod this. That's the amount that's currently in it. So that's the remaining, what we need to put in more, right? What we need to put in more. Very smart. Very, very, very smart. Very smart. Okay, yeah, that's very smart. Then we only need to record mask, and then we don't need to record on the side completed or the current side. Yeah, we're calculating the current side. Or the current side here is something you can calculate based on the return value. Oh, this is good. This is good. But I'm gonna stick to mine. Just with this little trick, so only 3 needs to be done. And then we also update the current side every single time. Yeah, so update from the official solution, right? From the official solution, learn that as long as 3 sides have been fulfilled, we can immediately return true. So that shall help us. So that shall help us save some more time. Also, there are other solutions in the discussion that only use state as the argument. The argument of the backtracking. Well, this is because they return, right, the current side, the side that has already been done is returned for each one. This is actually very neat. This is very, very neat. It's a logic. Oh, 90 minus 1. 0, and then say the current j is smaller, then we return this. Hold up. So the next mask is we take this value, so we don't even do anything. We just take this value, we'll go to the next one, right? And then basically we say, if we take this value, what would the remaining state give me, right? Give me in terms of the total. There's actually the total, right? There's actually not the total, the amount on the current basket, on the amount on the current side, what has been filled, right? And then I do this, I give my no fill. Yeah, it's a good solution. This one in particular is quite brilliant. Yeah, very good solution. But I like mine. it's clear, right? It's clear. We have current side, we pass everything, so I kind of know where things are. I do want to see if this can be even faster, because we are only checking. Yeah, that's actually on. It's not. It's n times, because I have n2 to the n states, but each state will have to do n times. Okay, so let's see if this one will be faster. We only have equals 3, so we save on 1. Yeah, it's even faster. Yeah. So I'll save some more time. Indeed, so this one runs at 124 milliseconds. But that'll be it. I kind of, it's getting late. Don't want to implement that guy's solution. So yeah, that'll be it. 73%. That's good enough. Yeah, that'll be it. I will. I'm happy. I think this one deserves to be a difficult question. Right? Anyway, all right. That's it. That's it for today. See you guys tomorrow. Adios.